Okay, so how many of you have actually implemented something like an FRP system yourself? So there are like 2 guys, and I think there's at least, yeah, or something like it. Doesn't have to be strictly FRP. So, so this talk is actually about a system that I wrote because I haven't actually been doing GUI programming for a very long time. So when I started working on a project, I wanted to figure out how to really write the GUI in a concise and readable manner. And I started out actually with the concurrent programming library based on concurrent ML ideas like PyCalculus, and it basically worked, but it was a bit too low level. So then I started looking into reactive programming and wanted to figure out what would be the easiest way to sort of make something like that. And this is the library that I'll talk about now is the end result. So first of all, a little bit of perspective. So this is an FRP meetup, but and we also heard that the classical idea is basically this time varying value. You have continuous time, and then you can just compute the value of your behavior at any point in time. But this is actually about the other side, which is the idea of having only sort of streams of events, and also the same thing that RX, for instance, does. So I wouldn't really call this FRP. I would call it like a discrete event stream processing. And a little bit more landscape. Don't take this too literally, but the idea here is that we have sort of a set of applications that we want to write, and then we have like different kinds of languages or libraries that we can write those applications with. So the largest circle here is like you have the full concurrent programming at your disposal. You have like CSP or PyCalculus. These are like concurrent programming models. And then the smallest circle here is where you have event stream processing libraries like RX and Bacon and the choice streams, which I'm talking about today. And then the smallest circle here is where you have like actual FRP systems like Elm and Regent and WebSharper, UE Next, and many others. Don't take this too literally, but there are a couple of important things here. So when you have like a very low-level system, it's very expressive. You can write many kinds of programs with it, but it's usually a lot more tedious and low-level. And then in the middle, you have some ways of organizing the mess into something more readable. And in the smallest circle, you have systems which give you very useful properties. Like in Elm, you have time travel debugging and very powerful features. But of course, the downside of having a limited system like Elm is that there are situations where it will just not work, and then you have to resort to some other technique. So I think that what makes RX and Bacon and choice streams and other similar libraries successful is that they are expressive enough for writing practical programs without actually going into two sort of pure systems where you just can't escape from the reactive world into the outside imperative ugly mess. Right. So what are these event streams? So here's basically a signature of actually sort of a simplified signature of what these streams are all about. So basically we have a type of streams which have this which basically carry values of the type X. And then we have combinators like map, which given a function from X to Y, you can map a stream of X's to a stream of Y's. And then we have many other combinators, very powerful combinators, like a merge map combinator, which basically takes a stream of x's and then it transforms each of those x's to another stream of y's and gives you a stream of y's. And the merge is done basically in a time-dependent manner, so that if you get a stream that gives a value, say after 100 milliseconds, and another stream that gives a value after 200 milliseconds, then you get a stream where the first value you get is after 100 milliseconds and the other after 200 milliseconds. And then we have other kinds of combinators like combined latest, which takes two streams, a stream of x's and y's, and then gives you a stream of pairs of x's and y's. It always takes the latest value from both streams and gives you a pair of those. And then also other kinds of time-dependent operations like a shift, which you basically give it a time span, and then when you give it a stream of x's, then after you get a value from the stream, then it actually is delayed by the given time span, and then the end result stream only gives the value after the time span. It sort of shifts the stream of values in time. Of course, ultimately what you want to do is that you want to do something with those values, and actually with the approach that I'm using, then it's not absolutely necessary to do things imperatively, but in practice most GUI frameworks are imperative. So what you actually do is that in the end, after you have composed the stream of events that you want, then you basically iterate all the events and do some sort of side effect with the value, like modify the GUI components, maybe change some button texts or whatever you want to do there. So let's actually look at something concrete. So this is basically a very simple application with which you can write these to-do items. And this has been done using the choice stream library. And all kinds of actions here are programmed using those streams of events. So when I push these buttons, then what happens internally is that some event is propagated through the streams, and then some action is taken to actually do something with the event. And what's sort of nice about doing this with the streams is that mostly we can think in terms of immutable state. So, for instance, in this applications, we actually hold the whole list of to-do items, or the map of to-do items. We hold it in a single variable. The whole state is actually immutable otherwise. And then when we do some action to modify the state, then we actually write it to the variable, and from that an event is generated, and then that event propagates to the handlers that update the view. So there's, for instance, like here is basically the stream that renders the view, which is like the list of events depending on the filter. So we get the stream of events from the model, and then we combine it with a stream that's the filter for selecting which elements we want to display, and then we only basically keep the preceding one. In this case, this actually doesn't make anything of value here. And then we subscribe our operation to it, and then we make sure that we execute code on the main thread, because in this GUI framework, all GUI manipulations must be done from the main thread. Then we clear the items from the panel, and then we go through the model and actually construct and add controls to the panel. then there are also other streams, like in the application there's this feature that that when we have the mouse on top of an item, then the remove button appears, which can be pressed. And this was actually the filter that we can select. So, so here we actually listen to the events corresponding to the mouse entering the control and then leaving the control, and then we combine those streams and actually calculate the value of whether the mouse should be on the control or not. And then, then depending on the visibility, we just set the visibility of the button. Right. Then there's actually another application. This is actually the original application for which, sorry, wrong key press. So this is actually an iOS application, and this has lots of asynchronous behavior. So for instance, when I click on this, then an asynchronous HTTP request is made to actually get the data that's displayed here. And also many other kinds of asynchronous behavior. All the items here are fetched asynchronously. When I do some operations here, like when I reserve the station, then a request is made, and due to the way that the backend works, then we actually poll for this information asynchronously, so that we don't keep any state in the client. But this application is also written using the same streams technique, and this was the original application. Right. So so obviously this allows us to in many very flexible ways to actually get to the when we start with the very primitive events, then usually none of those events correspond to exactly what we want to do. So when the user presses a button, an event is generated. But usually we cannot do something immediately after that event. We might need to combine that with information from many other sources. And what these stream combinators allow us to do is to do those combinations and then only do the action when we have all the relevant information. Right, so let's get back to the so what would be the sort of the simplest way to do this kind of reactive programming, to represent the streams and to implement combinators over those streams? So, so basically, one of the very first things that you learn when you learn about functional programming is the basic list. So basically you have list constructors where you have a nil, which denotes the end of the list, and then you have consists, which carry a value and then refer to the remainder of the list. So this is just a very basic linked list written in F#. And we can, of course, write many kinds of operations on those lists. So basically, a very simple map function. You give it a function, and then you give the list of x's, and then we can create a new list by mapping an operation, or actually like mapping the f over the x's that we could get from those consists. Can everyone basically read this syntax? I'll try to keep the samples very, very simple, basically. But of course, this just doesn't work. It's just too strict. We would need to know all the events beforehand, and there's really no concept of time. So what would be the next simplest thing is that we actually wrap the list constructors in a lazy value, sort of. So what's this lazy value actually? It's a type which can be constructed in two essential ways. We can create a lazy value from some given value, and then we can also do this bind operation, which when we give a lazy value, then we can actually return another lazy value based on the value of the lazy value, and then we get a new lazy value, and then we can extract the value from the lazy value. And the idea is that none of these operations are evaluated until or before you actually force the value to be computed. So this allows us to write a lazy map function. So the only difference here is that we do the bind instead of the usual function application, and then we return the results as lazy values. But this is structurally very simple. And well, it still doesn't work. So there's still no concept of time. So operations like merging two different streams time-wise just doesn't work. So what would be the next simplest thing? We actually replace the lazy values with promises. So how many of you are not familiar with the concept of promises or futures? So I think everyone understands them. So the basic way, or what the promises are, is that similar to lazy values, we can construct a promise with some value, and then we can do the same bind operations on promises. But then in this formulation, we have one additional operation here, which is the non-deterministic choice. The idea is that when you have two promises of the same type, then you can non-deterministically choose or create a new promise, which actually gets the value depending on which promise becomes ready first. So here's an example. We have a left-hand side promise, which is basically computed by doing a time out of 100 milliseconds, and then it returns left-hand side, and then right-hand side, which is a time out of 200 milliseconds, and it returns to the right-hand side. So when you combine left-hand side and right-hand side with non-deterministic choice, then and wait for the result, then what would the result be? So in this case, it most likely will be the left-hand side. There's actually usually no guarantee that it would be always the left-hand side, depending on how this promises would be scheduled. But usually you would get the left-hand side. That would be computed first. So what we can do with this non-deterministic choice is that we can write combinators like merge. So the merge combinator is given two streams. We have a stream ls and stream rs, and then we do a non-deterministic choice where we have on the left-hand side a stream which takes first from the ls stream, and then basically returns the left-hand side value, and then continues the merge. And on the right-hand side, we take from the rs stream first. So rs here becomes the ls, and so on. Is this something that requires sort of more explanation? I think this is very clear. So just to recap, when we do things this way, all lazy stream combinations basically still work. And we can write combinators using recursion, lexical binding, and immutable data types. And we basically pull those streams using concurrent lightweight threads. which are, in these examples, we are basically using the promises as the streams. As the concurrent threads. And by comparison, basically the implementation using these techniques is currently something like 700 lines of code. RX is something like 50,000 lines of code, and it doesn't have any sort of back pressure support. And RX Java is 30,000 lines of code. And there's actually this comment in the merge operation that this class is complex, and I'm not a fan of it despite writing it. This is written by the author of the RX Java implementation. So if we compare, then I'm not sure whether I would say that I would be proud of writing this, but it's very clear to me, and I find it sort of very simple and easy to reason about. So is this really enough? Do we need to extend the representation even further to make all the desired operations? So one of the interesting things is that some of the operations are quite tricky to implement, like group by and shift. For instance, shift is like the RX delay operation. And in fact, Eric Meyer in a talk in 2014 said that something like that he doesn't know how to do group by in a pull-based manner. But in fact, after that talk, it was implemented by RX Java and also by me independently in very different ways. And the truth is that those basic promises that we saw on those previous slides, they are not enough for some of these operations. Like in the group by operation, I use some other primitives also, and also in the shift operation. So actually the library of choice stream combinators is written on top of my concurrent programming library, which basically provides PyCalculus. And PyCalculus provides operations like the non-deterministic choice and synchronous channels and all kinds of nice things for concurrent programming. Another problem is that all the combinators that we saw previously were basically very functional. There was no imperative state anywhere. And of course, in the real world, we have GUI frameworks like in the VPF application and also on UI kit used on iOS, where we basically have observables or something that communicates using callbacks, and those callbacks usually only return nothing. So you cannot write any sort of functional code with those frameworks by default. So what we need to do, or need to be able to do, is that we need to be able to convert an observable into a stream. And the only realistic way is to actually imperatively add to the end of the stream. So for that purpose, that has been made possible. So actually in the actual library, promises are a type which is also there's also a subtype of promises which are like these write once variables, which can be created and then written to afterwards, and they can also be used as promises. But using those, we can write an imperative stream source where we can create a new stream source, and then we can add values to the stream source, or signal an error, or close the stream source. And then we can also tap into the stream source, and we get a stream out of it. And that stream has all the values that we put into the stream through the value operation. So, what are the benefits of this approach? Compared to RX, the implementation is really much simpler. We can use basically functional programming techniques in most of the implementation. And we also get all the lazy combinators, which is not true of RX, because RX is eager. So in RX there is, for instance, the generate function, which is a bit like an unfold, but it's the basic version is strict. It generates the values immediately after you subscribe to the stream. And then there's a special version of generate which takes a way of slowing down the generation. So there's a built-in mechanism that delays like subsequent values, and that is not necessary with choice streams because they're not eager. And then there are also new combinators that can be written for choice streams. Like for instance, this is just an example, key preceding one, which takes a stream and returns another stream, which works in the way that, let's say that this stream is a live stream of some sort of, let's say those button presses. So if we have a GUI where we can press the button many times, and then we will not be taking values from that stream, then the key preceding one would make it so that when we ask for the next value from the stream, then we would only get the latest value that was added to the stream just before the operation to pull from the stream. And this is actually not really possible in Rx, because in Rx you subscribe for all the values of the stream. So there's no way to just buffer one element and then you would just lazily get something out of the stream. You get everything or nothing. So using key preceding one, we can actually write many kinds of throttling and sampling operations. So for instance, this example, we have a live stream, then we keep the preceding one element, and then we pull on ticks from tick stream. So this is actually like sample before. We get a sample from the live stream before the tick. And this can be done in compositional way. Another benefit is that due to the way that the streams are built, basically, well, the actual library doesn't use promises everywhere. And there's like a more fine-grained types and operations for parallelism there. But because we have basically like asynchronous promises, then we can do asynchronous operations everywhere. So let's say we have a stream of notifications, which are basically just strings or messages of some kind, and then we subscribe or iterate the notifications. We get a note, and then we show the note, and then we can sleep asynchronously for 3 seconds, and then we can hide the note. And the key thing here is that this operation here is an asynchronous operation. It starts on the main thread and it also stays on the main thread. It shows the node and then it sleeps and then it hides the node, and after that the asynchronous operation is completed. And the important part here is that this iterate job combinator, it waits until this user-defined operation returns. So in Rx you cannot do this. In Rx, if you have a subscribe operation and then you do an asynchronous function after the or in the subscribe, then that actually returns immediately, and then Rx will push the next event even before the asynchronous operation returns. So what we basically get here is a kind of a back pressure way. So this is a very simple way of writing a notification system that always displays things at least for this 3 seconds. If there are sometimes happens that you have more notifications in the period of 3 seconds, then those will be queued and displayed. Each of those notifications will be displayed for 3 seconds. So if you want to do the same thing with Rx, you need to compose a much more complex stream to do it. And in fact, there are like asynchronous and synchronous versions of most combinators. Another thing is that these kind of streams are consistent in that every consumer gets the exact same sequence of values. And if you think about the representation, which is just basically a cons list of promises, and what you do is that you basically pull stuff from the cons list, and you may have many different threads or lightweight threads pulling from those cons lists. They all get the exact same values. In Rx, things work very differently. There's a subscribe operation, and subscribe basically potentially creates a new pipe for values, so to speak. And it's quite possible that different subscribers get different values. And this doesn't happen with choice streams. here's an example of basically a kind of bug that I've seen actually like a couple of times. The RX version here is sort of pseudocode. I've seen this bug written both in Bacon and RX. And the idea is that you're doing some sort of polling, and you create a stream that has events on those, or actually has like an event after every time span. And then you do an asynchronous operation in response to those timer events. And can you spot the problem there? Basically, the problem is that if it happens that this request takes longer than the time span, then actually you queue operations. And then you actually start doing many requests much faster than you wanted. With choice streams, because things work lazily, so we can have the asynchronous operations, and then we indefinitely repeat the operation. It gives us a different value every time, so it could be an HTTP request, and we get the different result from the request every time. And then what we do is that we combine with after each, and this works so that when we pull from this stream, then it performs the operation, and after that operation, it waits at least for that time span before it gives out another value. So it doesn't matter how long this request takes, there will always be at least this time span after each request, before the next request. So this is just a very simple example, but basically these sort of streams have sort of like a two-way communication between the producers and consumers because of the pull style. Here's another kind of bug that you often write with RX, is that you start some sort of process and then you subscribe for the outputs. And can you spot the problem? Well, the problem is, of course, that if you start something and then you start observing for the events later, then there's a chance that you actually miss some events. This doesn't happen with choice stream because the stream is basically immutable. When you have a pointer to the head of the stream, you will always get the same sequence of values from there. So it doesn't matter if the process actually creates a few values there, as long as you then start consuming those values so that they won't leak. Also, another specialty of RX is that when you have multiple subscriptions, then you often need to do something like publish and connect to ensure that both of these subscriptions get the same sequence of values. And that's also not necessary with choice streams. How many of you are familiar with the hot and cold streams of RX? Yeah, several. But not that many, actually. So with choice streams, we don't have actually like a hot and cold stream. But the way I would like to put it is that there are lazy and live streams. So a live stream would be like a stream that is generated from, say, a GUI button, where if we hold a reference to the stream head, then it might be possible that the button might be clicked several times, and then several events will accumulate there before we consume them. So live stream may accumulate events even when there are no operations pulling from the stream. And so if we don't consume it, then it basically leaks memory. Whereas a lazy stream does absolutely nothing unless you pull from the stream. So one thing that you can do is that you can convert live streams to lazy streams to avoid space leaks like that. Another issue concerning space-time leaks is that with these types of streams, there's essentially implicit buffering, and basically if you don't consume the streams, they will leak. If you happen to hold a reference to a stream head and you hold it in some data structure, and then more events are generated to that stream, then that will leak. And that cannot be prevented with Hitler-Miller type system. And also there's potential for leaks if you consume streams too slowly. About these two kinds of problems is that this usually don't happen because what you do with those streams is that you compose the stream and then you start iterating over elements of the stream or subscribe to the stream, figuratively speaking. So that naturally this doesn't usually happen. But it's quite possible to do something like this, that you take the zip operation of two live streams, and there's a leak possibility here if let's say that stream A would be faster than stream B. There would be more events in stream A, and what the zip operation does is that it takes always the same amount of elements from both streams. So if it takes like 10 elements from the A stream, it will also take 10 elements from the B stream, and if one of the streams is faster, then events will accumulate. So and one way to fix it is also to use something like the key preceding one combinator. And one thing I also experimented with is that I wrote a typed version of these streams, which has this phantom type for whether the stream is live or lazy, and actually prevents combinations like this. It requires you to do something about it. So, so just a summary of what to think about. So boss is push, leaders pull, you choose.
Well, first.